Hi guys, welcome to Lab 3 of Physics 2211, entitled Finding the Mass of a Black Hole. I'm Zach McGill, and let's run through a quick introduction of the lab. So, we are given the motion of a star orbiting a black hole of unknown mass, as well as the black hole's position. We are able to determine the forces acting on the star based on the position data. This is the opposite of previous labs, in which we found the object's position based on initialized data and known force. We will model the star's motion using a computer code. Then we'll discuss the use of FNet and change in momentum in the context of this problem, and figure out if this system could be used to find the mass of a different black hole. So here I had a few important pieces of code, but we're going to go ahead and just look at the code in whole. So up here you have some visualization and graph settings. Nothing too important. Our star is going to be a yellow sphere. Its path is going to be modeled by a green line. The black hole itself is at this position value. The radius is kind of a guess and check to see what it would look good for the graph. We have the star's mass here, as well as the change in time at each interval in seconds. Down here we have some code that takes the values found in stardata.csv and finds the changes in the x component of velocity as well as the changes in the y component of velocity. And now we get down to the actual physics, where we find initial velocity, initial momentum, final momentum, which obviously are the star's masses at the time, times the velocities. And then we can find the both the change in velocity and the change in momentum. And now we get dp/dt, and in this model we can just set fnet equal to dp/dt. We'll talk more about that later. Here we're finding the change in momentum parallel to the object's motion, which is all here, which is based on the derivative of the momentum, and again we can set fnet parallel equal to change in momentum parallel. Same with perpendicular. Perpendicular is just total momentum minus parallel momentum, and then we can set that equal to fnet perpendicular. Here's just some more visual things about setting up the arrows that'll show you the direction of fnet, fnet perpendicular, and fnet parallel. And then down here we have a little bit of code that finds the mass of the black hole, which we can look at once we run it. So let's run the module. So first you can see the star moving. It moves pretty fast. I apologize. Here are the arrows indicating total force parallel to the motion and force perpendicular to the motion, obviously, and then fnet is the force of gravity. So the arrows are definitely in the right direction. Here you have the black hole. Fnet is the gravitational force between the two. The fnet perpendicular is perpendicular to the object's motion and pointing toward the center of this imaginary kissing circle, and then fnet parallel is parallel but in the opposite direction of the object's motion. So also you can see here we calculate several different values, including velocity, but most important we can get the black hole's mass, which we just labeled it average mass. It's the same throughout. Moving back to the PowerPoint, just a few things. To find the object's mass, we used the gravitational force formula, which is big G times mass 1, mass 2 divided by r squared. So the rate at which momentum changes with time is equal to the net force applied to an object. In this case, we are using the derivative form of Newton's second law, where the changes in time interval and momentum are so small that they're actually the derivative of velocity, which is acceleration, which, as you guys should probably know, is Newton's second law. Force equals mass times acceleration. And there are often forces acting in a direction in which the star is not moving. So finally, we have our what-if question, which basically asks, if we put a different black hole in the same position and got new motion, could we find the mass of that black hole? And the answer, of course, is yes. The idea of the lab is that with each individual mass, we're going to have a whole different set of motion that we can use to go back and find the forces. However, this question in particular says that the star's motion will be completely unchanged. And because of this, it means that the mass of the new black hole has to be identical to the mass of the old black hole, because for each black hole of some mass, they're going to have a unique set of motion corresponding to their mass. And that's the big idea of this lab, is that we can work backwards with given motion to find the forces acting on an object. Thank you guys for watching, and I hope you enjoyed the video.